Welcome to Yurix AI. This is Lecture 4 of LLMs from Scratch, Zero to Builder. I am absolutely thrilled you're here today because we're tackling what is arguably the most exciting, foundational topic in modern AI. Honestly, whether you're completely new to this or just looking to really solidify your understanding, I've designed this explainer to be fully accessible. Think of me as your friendly guide. We're going to demystify this incredibly complex machine, break it all down, and make sure it makes perfect sense.
To kick things off, here are our learning objectives. We're going to cover these 5 sections in order. First, transformer basics. Second, a simplified architecture. Third, a note on attention. Fourth, BERT versus GPT. And finally, transformers versus LLMs.
Okay, let's dive right into this. Section 1, Transformer Basics. To really grasp modern language models, we've got to look back at the exact spark that ignited this whole AI revolution we're living through.
And that spark, it was a famous paper released back in 2017 called Attention is All You Need. Seriously, if you search for this on Google Scholar today, you're going to see well over 100,000 citations in just a few short years. It's wild. If you've ever wondered how ChatGPT was actually born, this paper right here is its origin story. It is incredibly rare for a scientific paper to have this kind of immediate, literally world-altering impact, but this one is the foundational building block for all modern large language models.
So, what did this legendary paper actually introduce? Well, it introduced the transformer. By definition, a transformer is a deep neural network architecture. But you know what's truly fascinating? When the authors developed this back in 2017, they weren't actually trying to build some all-knowing chatbot. Not at all. They were just trying to solve a machine translation task. Specifically, they wanted a better, faster way to translate text from English to German or English to French. Text completion wasn't even the main goal. It was all about translating one language into another efficiently.
All right, moving right along to Section 2, a simplified transformer architecture. Let's look under the hood.
Now, full disclosure, the original diagram in the 2017 paper is packed with some intensely complex mathematics. But for this explainer, we're intentionally leaving out the dense math to just look at the intuitive flavor of how this thing actually operates. We can break this simplified architecture down into a left-to-right journey with 3 major phases. Step 1, tokenize the input text. Step 2, embed that text via the encoder. And Step 3, predict the final output via the decoder. Let's walk through these step by step so you can see how a sentence actually gets processed.
Okay, before a neural network can even read a sentence, like, say, fine-tuning is fun, it needs that sentence translated into numbers. And this is exactly where tokenization comes in. Tokenization is that essential pre-processing step where we break down an input sentence into individual subwords, or tokens, and then we assign a unique ID number to each one. So for our purposes today, you can just imagine we're taking a sentence, chopping it up into individual words, and basically handing each word its very own specific ID badge. Now, what's really interesting is how we handle the actual meaning of those words. I mean, just having a bunch of random ID numbers isn't enough, right? The model needs to somehow understand that words like dog and puppy are related. And this is solved by vector embedding. Vector embedding maps those tokenized words into this massive high-dimensional space so that their semantic meaning and their relationships are captured mathematically.
When you visualize this in practice, it's pretty amazing. Words with similar meanings naturally gravitate toward each other in this giant mathematical space. So the vectors for king, man, and woman will cluster closely together. Apple, banana, and orange will form their own distinct cluster of fruits. Football, golf, and tennis will group up as sports. By converting tokens into vectors, the machine finally has a pure mathematical way to understand how concepts actually relate to one another.
So, what part of the transformer is responsible for all this heavy lifting? That would be the encoder. The encoder sits on the left side of our architectural journey, and its sole job is to take those raw, pre-processed tokens and convert them into those rich, context-aware vector embeddings we just talked about. Once the left side finishes encoding all that meaning, it passes those vector embeddings over to the right side of the architecture, into the decoder. The decoder takes those embeddings alongside whatever text it's already translated to predict and generate the final output. But the absolutely crucial detail to remember here is that the decoder generates this output one single word at a time. It predicts a word, adds it to the partial output, and then runs the whole cycle all over again to predict the next word. Now that we've got the pipeline down, let's move to Section 3, a note on attention. We need to talk about the absolute standout idea of that 2017 paper, because attention is, without a doubt, the transformer's ultimate superpower. To really understand why attention is so revolutionary, ask yourself this. How does the model remember context across really long sentences? See, before transformers, earlier models suffered from this thing called long-range dependencies. For example, if a sentence started with, Harry Potter was standing on the platform, and then 3 paragraphs later it mentioned boarding the train, well, earlier models would literally forget that Harry was the subject. Those early words would just lose their impact on later words.
The brilliant solution to this problem? Self-attention. Self-attention is a mechanism that allows the model to constantly weigh the importance of different words relative to each other, no matter how far apart they are in the sequence. It basically calculates an attention score for every single word, looking across the entire context to figure out exactly which words matter most right in that specific moment.
Let me give you an everyday analogy to make this super intuitive. Think of self-attention like reading a gripping mystery novel. As you're reading a scene in Chapter 10, you don't just process the current words in isolation, right? Your brain naturally casts its attention backward, weighing past clues, maybe remembering a suspect's passing comment from way back in Chapter 2, all to understand the current scene and predict what happens next. Well, self-attention gives the neural network this exact same human-like ability. It keeps the entire context alive.
So, the crucial point is that this mechanism literally changed everything. Let's jump into Section 4, BERT versus GPT, and see how this built into the 2 massive families of models that emerged from this architecture.
Let's compare them directly. While the original transformer had both an encoder and a decoder, BERT and GPT actually split the difference. BERT uses only the encoder block, while GPT uses only the decoder block. And because of this, their directions are completely different. GPT reads left to right, trying to predict the very next word in a sequence. BERT, on the other hand, is bidirectional. It looks at sentences from both the left and the right simultaneously, because its main task is to predict masked or hidden words missing from the middle of a sentence.
Because of these differing architectures, they have entirely different best use cases. BERT is excellent for tasks like sentiment analysis. Since it reads bidirectionally, it understands deep nuance. It knows exactly whether the word bank refers to a riverbank or a financial bank, based on the surrounding context. GPT, on the flip side, is an absolute engine for creation. Because it's optimized to continuously decode the next word left to right, it's phenomenally good at generating brand new text and completing open-ended prompts.
Which brings us right to our final section, Transformers versus LLMs. I want to spend a moment here to clarify a major point of confusion for beginners, because out in the real world, you're going to hear these 2 terms used completely interchangeably all of the time. But technically speaking, they are not completely interchangeable. While it's absolutely true that, colloquially, a modern LLM is fundamentally a transformer trained at massive scale, the technical taxonomy is actually distinct. So remember this: not all transformers are LLMs, and not all LLMs are transformers. Let's look at that first part. Not all transformers are LLMs. The transformer architecture is so powerful that it's actually broken out of just language. We now have vision transformers, or VIT, which are actively used in computer vision. They can analyze images to detect potholes on roads, and they are incredibly effective at classifying tumors as malignant or benign in medical imaging. These are absolutely transformers, but they are certainly not language models.
Conversely, not all LLMs are transformers. Before 2017, we were still building language models that could do text completion. But those early LLMs were built on entirely different architectures, like recurrent neural networks, or RNNs, which used feedback loops to remember sequences. There were also long short-term memory networks, or LSTMs, and even convolutional architectures. They were all language models for sure, but they lacked that incredible self-attention superpower of the transformer.
All right, let's do a rapid-fire recap of our whole journey today. We learned that transformers originated from a 2017 paper primarily meant for language translation. The simplified pipeline runs from tokenization to the encoder for vector embeddings and finally to the decoder for output generation. We discovered that self-attention is the ultimate superpower, allowing the model to track long-range context. We saw how GPT acts as a decoder to generate text, while BERT acts as an encoder to deeply understand context. And finally, we clarified that while overlapping, transformers and LLMs are distinct concepts.
It's wild to think that simply giving machines a mathematical version of human attention was the key to changing the landscape of artificial intelligence forever. What will they pay attention to next? Like, share, subscribe to Yurix AI for a new lecture every day. Hit the bell.